All right, so hopefully everybody's had a chance to take a look at the homework B1. We're going to be doing a lot more help with that here. So last time I kind of explained the general theory of how to do homework B1, and we're going to work an example that looks just like the hand simulation from B1 here. So that's kind of what is on the agenda for today. Generally, announcements here. So there's this new ICA C1 available. Due before lecture C1. Homework B1 is out here. It's due relatively soon. Make sure it's clear and easy for the grader to grade. Two very different parts. One where you're coming up with examples, the other one where you're doing this hand simulation that we'll talk about here. So just some general comments about trying to make it easy to follow your submission. Some hints in question one. I'm expecting at least 2 examples of each category. Sometimes that's hard to do. Sometimes your mind just goes to one entity type, for example. And I've given you a tip that when it comes to entities, try to think of attributes that might differentiate entities and then think about, actually, are there ways I could break those entities up? So for a restaurant, if a restaurant was the system, then you can imagine that you might have virtual customers that phone their orders in or app their orders in. You might have customers that are showing up to the store. So there might be in-person customers, there might be customers that are online. So those are there. You're on 2 examples right there. So, similarly, there could be any type of service, any type of that sort of system. There oftentimes are going to be different modalities, different ways that the entities you're providing the service to can connect with. So maybe they come over the phone, maybe they are, an online entry, or maybe they're in person. Maybe there's a mail option. All of these different things could be different types of entities. And then likewise, once you start breaking up the entities, you can start breaking up the resources. So you could say that, yeah, in theory, there could be one resource cross-trained for every type of entity. But in reality, if I'm dealing with someplace that takes mail orders or like bills, like somebody's sending in checks to pay bills, or they might be paying them online, the infrastructure for processing those paper checks that people send in is probably very different. So you could imagine there's resources that could create different sorts of delays for those paper-based inputs than there would be for the virtual inputs. And so those now you got 2 different resource types. Before you just had one person handling, or one type of resource and handling that. But now that you have 2 types of entities, maybe you have to have 2 types of resources. So you can break a single resource or a single entity up, and that maybe helps fulfill this at least 2 examples, which otherwise might be hard to think about. I give other examples here, this is more abstract, but, taxonomically, you have animals, but there are different types of animals. There's dogs, cats, birds, humans. So all of those. So if you are modeling a system, that has an animal, like you're modeling a vet's office, a veterinarian's office, and there's different animals coming in the door. Well, now you can break those up and say, well, some people bring their dog in, they bring their cat in, they bring their bird in, and then all those can be different entity types. Passengers, and then you can break those things up. They're priority passengers, and they have a different process than business passengers or economy. These are things that theoretically we might be able to stamp as attributes, but for the purpose of the assignment, we should consider the alternative way is to just make them separate entities. So that's a tip there. In question 2, the hand simulation, where we're going to do an explicit example of today, these are just reminders of the things that come out of the textbook. So question 2 asks you to refer to a particular problem in the textbook for definitions of state variables that it asks you to populate. And these are those definitions just as a reference. So LQ is the number of customers currently at this time step waiting in the queue. LS is the number of customers currently being serviced at this particular time. So the sum of those 2 are kind of like the work in progress for the system, the total number of customers currently tied up in the system at this time. So in D, this is this other one here, in D, that is the number of customers who have departed the system by this time. This is one of these things that we refer to as a cumulative statistic instead of a state variable. It's not really capturing the state of the system, but it's keeping track of what has happened in the system up to this point so that you can then do key performance indicators or general performance statistics afterwards. So knowing how many customers have gone through the system by this time helps us at the end to say, well, what is the average amount of time a customer has spent in the system, for example? Or if I ran multiple replications, so I did a hand simulation with one table of data, and then a hand simulation with another table of data, and so on, I could say each one of them I was only simulating for 11 minutes, but what is the average number of customers that went through over all of those? So it's not a state variable, it's a cumulative statistic. It's something that builds up over the whole simulation run so that you can run stats at the end of the sim. So that thing there, and I'll show, give some tips on these, that is always going to be growing. Every time someone departs, that goes up by 1. Likewise, there's this sum of response times. This seems like a funny one to keep track of because it doesn't have a physical interpretation until you think of it as a numerator in an average that you'll take later. So this is like what we refer to as the response times, which we'll go into here in a moment in our example. The response time is the total time a individual customer has spent in the system from their arrival to their departure. So that includes how long they waited, as well as how long their actual service took. So as customers depart, we add their response times to this accumulator S that starts at 0 and it keeps growing. So one customer might have spent 7 minutes in the system, so S will go up by 7. The next customer spent 5 minutes in the system, S will go up by another 5, and so on. So we get this accumulation of time that our customers have spent in the system. Once we have both ND and S afterwards, then if we divide S by ND, then we get the average response time. So that's a reason why we keep track of this weird thing, is it helps us calculate a statistic later. So that's another cumulative stat. And then the last cumulative stat you have to worry about is the number of departed customers who have spent 5 minutes or more in the system. So this is another count. It is always less than ND. When it goes up, it will go up at a departure. So when someone departs, you ask, was their response time greater than 5 minutes? Did this customer spend longer than we want any customer to spend in the system? And if they did, we're going to increment this counter F. Otherwise, we only increment this one. So sometimes both of these counters will increment, sometimes only ND will increment, but they only increment on departures. So that's the definition of these things here. And then you'll have to keep track of these. And we're going to show an example of how to keep track of these in our hand simulation and further on here. But are there any questions about these definitions for those who've taken a look at the homework? Does that clarify things? All right, and as questions come up, of course, feel free to let me know. So other tips here, you notice in the table, and we'll see this in the example we do here in the slides, that the interarrival list is longer than the service list. So we have interarrival duration, and again, we'll see an example of this in a few slides. And then we have a list of service times. And there are one fewer service durations than there are interarrival durations. And that's on purpose because the idea here is that the first customer does not have a service duration so in other words, I think this is supposed to does not have an interarrival. The leading interarrival duration, I'm sorry, I skipped, I missed, I flipped that. There should be one extra service duration than interarrival duration. And that's because the simulation starts on the first customer. So every customer is preceded by an interarrival duration, except for the first customer, because we start the simulation on the first customer. So the interarrival duration that preceded that customer is in the past. We just don't even worry about that. That's the reason why every customer gets a service time, but only the second customer and forward gets an interarrival time. That's why there's a gap in that first. There's no leading interarrival time because we assume the customer we start at their arrival. So that's not a mistake. So that's a frequent question I'd get, like, oh, I think this is weird. There's a space here. Was there a number that was supposed to be there? No, that's on purpose. Now remember that later on in the semester, I'm not going to give you lists of times. they will be generated automatically because we'll have probability distributions they're drawn from. Because we're not there yet, I have to give you these lists. But these lists are sort of artificial. They're just there to get us used to the idea of how the simulation system works. Okay, so that wasn't a mistake. The other hints, you're going to be building a future event list in your hand simulation. If you've done everything correct, then at the end of your hand simulation, the FEL, the future event list, will have exactly one arrival in every row. It won't ever have two. It won't ever have zero. There will always be an arrival because we assume that the arrivals never stop. So you can always schedule a new arrival. You assume that whenever you process one arrival, you immediately schedule the next arrival. So there should never be more than one arrival, and there should never be zero arrivals. So if you look down through your hand simulation and your FEL is missing an arrival or has too many arrivals, then something may have gone wrong in your calculations. So that's one tip. Likewise, the FEL will have no more than one departure. It can't, it can have no departures. So it may be that just right now the system's idle. So no one's in the system, so we have no idea when the next departure will be. So the future event list, which is the event calendar, it may not have a departure, but it can't have two departures because we only have one server in this system. So there can only be one departure at a time. We only have a resource capacity of one, so you can only schedule one departure at a time. So if you see more than one departure in your FEL, then you've maybe done a calculation wrong. Maybe you've accidentally left a departure from a previous time in the list, something like that. And don't try to think ahead and pre-schedule departures. You only schedule departures when an entity moves into a server and you know that that entity will be departing and that's guaranteed. So don't like try to simulate in your head. You want all the simulation to be done on paper or on screen in the table. And then the clock will always match the time in the first event record in the FEL. So as we'll see when we do this example, in that first row or in every row, there's going to be an FEL, an event calendar, a future event list. And the leading event in the event calendar, in the FEL, in the future event list, will have a time. And that time will always match the current time because in the next row, because that future event list is setting the evolution of time in this universe. So in the previous row, you're saying the next event that happens is going to happen at time 6. So that should mean that in the next row should be time 6. So if you look at the FEL, you should be able to see that. It's like a copy and paste that whatever was the time on the previous FEL's head will be the current time in the next row. So that's another thing to look for. So quick spot checks that you've done the sim right. Other things, LS plus LQ, those two state variables will always equal the number of total customers in the checkout line. So this checkout line state variable keeps track of the customers being processed as well as the customers waiting. So if there are 5 people in your checkout line and LS plus LQ equals 4, then you haven't updated your LS plus LQ correctly, and you should go back and check that. Also, these cumulative statistics, they're cumulative and in many cases, and definitely this case, they're non-decreasing. So every departure in D goes up, it never goes down. Some departures, F goes up, it never goes down. And at every departure, S goes up, it never goes down. And because F only goes up at some departures, F will always be less than, or maybe at first equal to ND. And the response jumps will be larger than the corresponding service duration because of waiting time. So services say this customer is going to be in the server for 4 minutes, but their response time is coming out at 8 minutes. Well, that's because they had to spend 4 extra minutes in line. And we're accounting for that in the response. Scheduled your events, forget that the service timetable exists. That, remember, in the future, we're not going to get them. from all you'll know is whatever you stamped the entities with in terms of their attributes. And we're going to stamp these entities with their arrivals, their arrival times, and their departure times, and look at the difference between them. That's how we get response time. And that should be larger than the service time that it was associated with that entity, because most of these entities will have to wait because they will arrive to a busy system. So those are spot checks that after you do your tables, you should be able to run through those. I've also put a bonus question that's a couple extra points. You don't have to do, but it basically asks you to say, take your hand simulation. And this hand simulation, you might use a spreadsheet to organize it, but you're not supposed to be using any formulas in the spreadsheet. It's just a table at that point. And so that's what we mean by hand simulation. You are the one doing all the calculations. But in the bonus, I ask you to build a spreadsheet following another example from the book. And this is something that I'll show you next time to give you a hint of how to do this. But if you do this example like in the book, where you're basically going to load the service times and the interarrival times into your spreadsheet, it will automatically populate all of the numbers that correspond to this simulation, but it'll be in a different format. And that format, though, should have the same information if you know how to parse it. So if you're looking at that spreadsheet, you should see the same things from your hand simulation show up in your spreadsheet. So if you do the bonus, leverage the bonus to spot check your work on the hand simulation, because they should match. There's nothing different about the bonus versus the hand simulation. The results should match. Any questions? Just hints on the homework. Okay. I mentioned before, I'm just going to have this up here for all of September. If you're interested in the arena competition, that which you can use as your final project, that is available to register for until the end of the month. Lots of information on this slide. There's a link here. It'll tell you more about it. And there's also someone at IIC who can answer for additional questions. So session entry forms are due at the end of September. So there is also a winter session that starts out at the start of January. So even after this class, if after you do this class, you figure you enjoyed it and you'd like to try this out, then you can also do it next semester. And that also reminds me, we haven't been offering 475 lately in the spring. So this is sort of a weird segue to this, but it's rare, but occasionally we do have students that are caught, plagiarizing old work or those sorts of things. And we're obligated to report it. And a lot of times we report it and we find out that that student has had another infraction. And at that point, the dean's office doesn't give us any choice but to fail the student. And then in the past, 475 has been offered in the fall and the spring. So then a lot of times they would just take it in the spring. Well, now if that happens, you have to take it in the next fall. So that can create complications for graduation or whatever. So I don't think there's a lot of really difficult burdens in the homeworks in the labs. There's lots of drop policies. We provide lots and lots of help. So do your best to make your work look as independent as possible, because just know that there's no plans to offer 475 in the spring. I just mentioned the spring kind of reminded me here, and it sets up some unfortunate graduation issues, but there's nothing we can do about that. So just try to do your best at representing your own understanding of the material, and you're going to be fine. It's rare that this is an issue, but when it's an issue, this is commonly the follow-up issue is that because I've had some sort of issue in another class, and now the TA noticed that my work was very similar to someone else's work, and now I'm in this unfortunate situation where the dean's office tells us we have no choice, that we have to give you an E, and then at that point, then you're stuck because you can't retake the class in the spring. So just something to keep in mind. It's a darker topic, but I just didn't realize I didn't mention it before, so just keep that in mind. Okay. So any questions? All right. So discrete event system simulation. So just as a reminder, these are the types of systems that we're working with. We've got lots of things moving around, competing for lots of resources that they all need in order to complete their whatever that process is. So we've got here at this crosswalk, we've got cars on the roads. This car cannot get to where it's going without using the crosswalk. So using the road that has to drive over the crosswalk. So if there are pedestrians in the crosswalk, then that car has to wait. Likewise, if there's cars in the crosswalk, the pedestrians have to wait. Bikers, similar situation, but maybe they have slightly different rules that they follow, but they also have to wait on these things and are waited on. So the entities aren't really waiting on the entities exactly. I mean, indirectly they are, but they're waiting for access to the resources that the entities are using. So this is an example where we have multiple, like in this case, I would say there are 3 processes that are sharing several resources. So the car process has car entities that it generates and collects, and it only needs access to the road resource. But the bike, process that generates bikes, it needs access to both roads and bike paths. And the pedestrian resource, they're only on sidewalks, but sometimes sidewalks actually end up overlapping with roads. And so I really should probably have this, that pedestrians need sidewalks and roads. And so whenever you have an entity that has claimed temporary access to one of those resources, then at that point, anyone else that needs that resource has to wait until that entity has stopped using the resource. That is the fundamental problem that we're trying to solve in almost all of these discrete event system simulations, is how to engineer the systems to reduce the amount of waiting, to reduce the amount of delay. Delay is our fundamental output of all of these systems. So when we're modeling these systems, we have to be good at noticing the entities and the resources, because those resources, those are the things you wait on, those generate the delay. The delays are the things that we analyze. Those are the major outputs. So, so that's kind of summarized here. So let's kind of have some practice at doing that. So this is our general rule here, is that if something is waiting in order to move along and then otherwise it will never be seen again, it's probably an entity. If we're asking a question about performance, or if performance experienced, we're probably asking a question about an entity, but not always. Resources perform service activities. And so if there's something that is always in the system offering a service, it's probably a resource. We can ask questions about resource utilization. How idle is this resource? How often is this resource idle? That certainly happens. And then activities are the things that take time. So when the resources are busy, how long is the resource going to be busy for that one activity? So that activity represents an entity has entered the resource. How long is that entity going to be in the resource, thus preventing the resource from being used by any other entity? That's what we mean by activities. And then delays occur because of a misalignment of activities. This activity happened, and a moment later, another entity would like to have used that resource so that it could run its own activity. But those 2 activities can't happen at the same time. If there was a way to somehow reshuffle them so that that collision didn't happen, then that would be good engineering. So that's part of what we do as operations researchers, is try to align activities to minimize delays so that things are nicely interleaved instead of competing. Okay, so let's do some examples of that. So here are just a couple of examples that all surround this real world system, the real world set of processes related to international cargo shipping. So I'm going to see shipping containers. I'm going to see container ships that have a bunch of these containers on them. And I'm going to see docks that unload and load these things up. And I'm going to ask different questions about different aspects of this system. And based on the question that I'm asking, I'm going to model the system differently. What's an entity and what's a resource kind of varies from the question. So let's see an example of that. I might say, on average, how long does each container take to reach its destination? So the idea here is that containers are flowing through the system and they're being delayed by ships that carry them. So what do we think is the best candidate as an entity in this model? What are our entities given this question? Containers. Why are containers entities? It's going through the system, and its speed at going through the system is being delayed by the system like a valve. But it will, every container, its identity is ephemeral. Like it's there and then it's not. And we care about the stats that it generates, but we don't care about the container itself. So we would think the container is an entity. And then that would mean that the things that delay the container are the resources. So containers are entities. So they allow for tracking individual container time. So really care more about the times that are generated by each container than the container themselves. And the ships and the resources are networked into shipping routes, and all of these things play into this resource. So like really, we could just say the ships are the resource, and the routes we can also kind of think of as another type of resource. Like why isn't the ship here right now? Well, its route is congested. So the ship is at sea, it would like to come in, but right now there's too many ships on its route, so it has to wait. So in this case, it almost seems like the ship is an entity, but we don't care how about the experience of the ship. We just care that the ship is not here. So for this question, we're focused on the container as the entity, and it just happens to be that this ship is almost like, it's sort of it's just being reused. So it's sometimes it's in LA, sometimes it's in Japan, it just goes back and forth. And so it does get delayed itself along the way, but in the whole scheme of things, we're thinking of it as this resource, which is sometimes here and sometimes not. And when it's here, we can use it, and when it's not, we can't. So even though the ship is moving, we still view it as kind of a resource because it's always the same ship and it's always the same shipping route. But whether it's available to take a new container that's the question. So the new things, those are the entities, the old things, those are the resources. And the ports, we don't necessarily need to explicitly model all of the activities at the ports, like the time it takes to load a container onto the ship. If we zoom out and we're looking at delays in terms of days, for example, if it takes an hour to load up a container onto a ship, then maybe that's noise. And we don't care about modeling all those fine-grained details of how long it takes to get a container onto a ship. All we really care about is how long it takes for a ship to get to its destination, and that includes how long it takes for a ship to get access to a route, and so on. So at the larger scale, we might abstract away all of these fine-grained details. We don't care about, well, okay, so the arm that picks up the container and it moves it onto the ship, well, that takes a certain amount of minutes to do that operation. Like all of these small things we can put into a probability distribution. We can just have a loading time distribution, and that will take the place of all of that. We can like put a stopwatch and we can say, well, how long does it take for the ship to go through all of these activities? And we can say, once it's done with all of those things, we're going to take that as our time. We're going to put all those times into a histogram, get a distribution out, and that models the loading process. And all of the details we just forget about because they're in the bell curve that we come out of that thing. So that's what I mean by abstracted away into the parameterized randomness. So questions about that. So this is, we can build a simple model at the large scale where we just have ships as resources and containers as entities. And the process of getting the containers onto the ships is an activity. And the process of the ships moving around is an activity. And that's all we need to explicitly model in our sim. We have to get the activity durations right. And that means talking to domain experts that know about all the fine-grained details. But we can ask them, overall, how long is it going to take for this ship to get from LA to Japan? And they can give us that. They don't have to tell us about, well, sometimes there's weather, sometimes there's this, sometimes there's that. They can just give us the distribution, and then we'll take that distribution and forget about all the details. Questions about that? Does that make sense so far? We can contrast that with a different question. What is the longest duration a ship will stay at one port while loading and unloading? So now we're zooming in a little bit. So we're not focusing on the global, like how long does it take for a container to get wherever the container needs to go? Now we are focusing on port operations. So when we're talking about port operations and our question is about a ship, then that suggests that maybe that the ships are being delayed by activities. And so containers and ships are different types of entities. So there's containers that arrive and there's ships that arrive and they get combined. And once you have a container, a ship filled up with containers, it can leave the system. And once it leaves the system, we don't care if it comes back. We don't care where those containers go. We don't care if the next ship we see is actually a ship we've seen before. Because what we're focused on, our boundary of the system is so narrow now, we're just focused on this port. Like, oh, an empty ship has arrived. Containers are here at the port. How long does it take to get these containers onto that ship? And once that happens, everybody goes away and we forget that their identity, we just kept track of the stats. It's like Moneyball or something. We're just watching for this individual game, how well did the players play? And then once the game is over, then it's almost like the teams move on and a new team comes in and we then do the same stats, not keeping track of whether this team has any relationship to the old team. So that's the idea here, that the containers and the ships are entities. The ports are resources that allow the ships to get loaded with the containers. So the port is a server. It becomes free when the ship becomes full and allows another ship to come in. The loading still is an activity performed by the port. So we can still model away a lot of the really fine-grained details of, is there a foreman on board directing things? What are the group dynamics of all of the different people involved in the loading operations? We can just put that into one big distribution of like, this team takes this long to get a container on. So when we have 50 containers, the sim will tell us how long this team that we know how they work for one container gets 50 containers on. And we don't have to worry about those fine-grained details. So again, we abstract away that, we get them kind of modeled in the probability distributions, so we don't have to build every little thing. So we've added a few more entities, we've changed our resources, but we're still hiding a lot of fine-grained details. Yes?
Waiting on
Mm-hmm. That's a great question. So the question was, if ships are waiting on containers, it doesn't seem like containers are resources, because it's like the ships are waiting to use the containers. But that's the thing, is that the ships aren't waiting to use the containers. The ships it's not like the containers are always there and a ship needs to come by and use the container and then free up the container for another ship to use. It's a resource is something that can be freed up for another entity to use. In this case, we're talking about entities that combine into batch entities afterwards. And so in your lab too, you're going to see this with muffins. So muffins arrive at an oven, those muffins combine into batches, and then batches leave the oven. And that's what's basically going on here. But instead of having the same types of entities, you have two different types of entities. Oftentimes when people model, for example, fast food restaurants or similar such situations, you arrive, or the customer arrives at the window, and then they put an order in. Oftentimes the way that's been modeled is the order becomes an entity that like springs forth like out of the side of the customer. Suddenly there are two entities in the system. And that entity is now inside the restaurant, that order, and it's getting processed. The entity outside the restaurant is now sitting at the window, waiting to get its order back. And so at that point, the outside is waiting on the inside, but once the inside and outside meet, they both disappear. So the fact that they disappear and are not being used by any other entities later makes them entities. if there's a possibility that another entity needs that resource right there, then it's a resource. So resources are about reusability. Does that answer? That make sense? Luggage is another example too. When you model people bringing luggage to an airport, you often model them as a batch. So it's like the opposite. It's a little bit like the opposite of your muffin simulation in lab two. They arrive together, kind of like the fast food. You arrive with your luggage. And then you then come up to the security line, you send your luggage through one process and you become two entities. And so the batch gets broken up. And then at that point, then you go through, and then eventually you have to wait for your luggage. Then your luggage comes back, and your waiting time certainly depends on your luggage, but you're not using your luggage. No one else is waiting for your luggage. Only you are waiting for your luggage. So it's like there's a part of you that's missing, and you have to wait there until that part of you comes back. And then once it comes back, you both can leave. So you're both entities. You just got broken up into two parts for a short time. Any other questions? Okay. Last one here. So when opening a new canal, will opening a new canal increase the number of total ships unloading at ports per day? So now this is a bigger question. And so we're talking about that ships are being limited, they're being delayed. And the hypothesis here is that part of the reason why it's taking so long to get a ship from source or from origin to destination is because there aren't enough routes available, or rather that there is a canal that is being backed up, traffic is being backed up at. And so you would like to build a simulation to see if this bottleneck is really the key limiting bottleneck. And so your simulation is going to treat the ships as the entities to be counted, but we now don't care about their containers because it's just a ship gets loaded up. We don't care how heavy it is, how many containers on it, because a ship with no containers takes the same amount of time to get through a canal as a ship with many containers. Maybe there's slight modulations that have to do with weight. We can deal with that. We can make the number of containers an attribute of that ship, and we can use that attribute to maybe delay the time it takes to need to get through that canal. But we don't need to keep track of all of the individual containers. It's just a heavy ship or a light ship, and that's all we care about. So ships are the entities. Those ships compete. So it's the competition that really makes a resource. Things have to compete for a resource. You don't compete for access to your luggage. You don't compete for access to an order, your order. But you do compete for access to a port or a canal. So these are types of resources. And so when a ship needs access to a port, we either give it the port immediately or we wait for all the ships to clear from the port before that other ship can come in. Same with a canal. Now, container handling, we don't care about the containers, as I mentioned before. So all of these, and we also don't care about the details of the canal operation. So, if you're coming up to the Panama Canal, there's a bunch of these locks. They're filled with fresh water. There's all of these different processes. The fresh water itself might be limited by the amount of rain that Panama has had, and that might change the operations of things. There's all of these details that we theoretically could build a fine-grained model of. That would be a high-resolution model of how the world works. But it wouldn't really change our ability to answer this question. And it might even make it harder to answer this question. So this is an example of where you actually get more benefit out of making the model simpler by making the boundaries of your system smaller, because then it's easier to reparameterize the probability distributions for the activities than it is to totally restructure your system. Like you can say, is this delay caused by the lack of rainfall in Panama? Or is this delay caused by a political change in Panama? All of these different things, you could build a high fidelity simulation that included rainfall and politics and all of these other things, and they all would factor in to the delays of the canal. Or you could just come up with an activity distribution that has 2 or 3 parameters. And if someone said, well, what if, tariffs or something else changes? Well, you could say, well, what change would they make on this 3-parameter distribution? It makes it much easier to simulate the possible effect on canal operations, because now you don't have to build a hyper accurate model of geopolitics and hydrology and all these other things. because all those things are abstracted away into this intermediate, into this delegate, this probability distribution that only has 2 or 3 parameters that you can change in very defensible ways to model that effect that happened in the world. Questions about that? Different ways to form entities and resources for the same types of systems. Okay, a lot of creativity comes into modeling. There are different choices that could have been made here. And you could defend why your choice was more elegant for answering that question. A lot of times it comes down to really formalizing what hypotheses you're trying to test. And under your experimental design, what predictions would you make under those hypotheses? And some, the same hypothesis with you can generate predictions for different experiments. You could say, I'm testing the hypothesis that another canal opening will have this effect, and or the canals are the limiting factor here. Well, you could imagine I could build a simulation that captures some aspect of the system, and that would lead, the canal limitation hypothesis would lead to some predictions for that system, but there'd be a different system that might simulate some other aspect of it that also is related to that canal limitation hypothesis, and that'll make different predictions. So you might build different experimental models to test the same question. That might be what you do to validate your answer, or it might just be that your flair for modeling just happened to be that you were more attracted to one experimental setup than another, and you do have that freedom to have that creativity, just so long as you can defend your choices. Okay. So, general feature: entities move in the model. Often they're moving in the real system. Resources are the things you're competing for. So entity arrives, entity leaves, you compete for the resource. A vacuum is a mobile resource picking up stationary entities. So it doesn't necessarily move in the real system, but hopefully you still see that the things that are arriving and leaving the system are the dirt coming into the vacuum, and the dirt is competing for access to the vacuum because it's a limited vacuum. So competition, the thing you're competing for is usually the resource. The things that are doing the competing are the entities, regardless of movement or not. So any other questions about this before we move on to our examples, like the homework? Okay, so the hand simulation example from the homework is basically inspired by a simpler version of what we did last time with the car wash. So in the car wash, we built this timeline, and we said that there are transport delays. There are delays from going from the entrance to the complex to the wash. There's delays from going from the wash to the vacuum station, and then there are activities going on inside the wash and inside the vacuuming. So it's a network of these nodes, different nodes with different characteristics for how they slow things down. But it's just this linear network, and we can model what goes on as this calendar of events. And I'm not going to go through all of these in detail because we're going to go to another example, go through in detail, looks more like your homework. But just as a reminder that, we built this by saying that you start out knowing that there is an arrival. You scheduled car A arriving. You also scheduled the end of the simulation over here. Those two things are scheduled simultaneously at the start of your sim. That's the only thing you know that happens. But then you let the logic generate the rest of the calendar. So what do you know at that instant of time, and what does that tell you about the immediate future? If you know that you're at a time step where a car arrives, then the things you know is that in the near future, that car will move to the car wash. So we schedule how much time we think that car will take getting to the car wash. We also know that if that car has arrived, then we can eventually we'll shift our focus to the next car that arrives. So we have to schedule when the next car arrives based on our historical data on how long traditionally do we see between cars that arrive. That is some distribution that we draw from, and then that ends up setting that thing up there. So, and at that point, you say, what else do we know? That's all we know at that time point. At that time point, we just know in the near future, the car is going to hit the car wash and another car will eventually arrive. And that's all we know. And that's where we can stop in our scheduling and then move on to the next thing in the calendar and do that over and over and over again. And that's what we went through last time. And as we do this, eventually we find times where the durations in between events are not set by things we knew ahead of time. And that's the generation of delays. So at this point in the schedule, we said that, the car B at this point here was ready to enter the car wash, but the car wash was busy. So we had to put the car B into a state variable to keep track of how many cars are waiting. And when we eventually gets to the point where car B can go into the wash, there will now be this gap between when the car was ready and when the car actually got to receive the service it was waiting for. That is something we couldn't have predicted ahead of time. There's no distribution where that red duration comes from. And that red duration is a delay. That is the output of our system. And so that's what we're trying to generate, these outputs, these delays that are generated there. And I don't think I see any other delays in this example, but that's what we'll end up seeing. As you go through your hand simulation, you're going to see multiple customers arriving and only one or two of them getting immediate access to a server. The rest of them are going to have to wait. And those waits, those wait times, those conditional delays, those are the things that we're trying to generate. That's what we've learned. We didn't learn about the interarrival times. We already knew about those. We didn't learn about how long each service takes. We already knew about those. But we combine them into a network. And what we learn about the waiting times. And that's the key difference between activity and the delay. All right, so before we drill down to that hand simulation example, like your homework, any questions so far about that car wash example? Okay, so let's do a clicker then. And the question I'm asking, I'll do a short answer. And so question for this clicker is, what are the outputs of discrete event system simulations? What's a simple word or words that captures what we mean by an output of a discrete event system simulation? Are the outputs the entities because they're flowing through? Are the outputs something else? What do we as operations researchers view are the key outputs, the things we learn from discrete event system simulation? And I'm not looking for correctness, I'm just looking for it having to be an appropriate answer. It makes sense as an answer. So don't put two in, I'm looking for a word. What are the outputs to discrete event system simulations? It's what I was just rambling on about. All right, so speed it up a little bit. One, two. All right, I'll leave that up for another 10 seconds. About 5, 4, 3, 2, 1. So I'm going to hit stop now. All right, what answer? What was I looking for? What was the right answer to that? Anybody? Delays is what I was looking for. Delays are outputs, activities are inputs. When we're going to talk about input modeling for the rest of the course, we're talking about how do you build activity distributions. Activities are inputs, delays are outputs. Entities are just water flowing through a fountain. We as engineers build the fountain and we study how quickly it takes to fill. That's what we're doing. We're studying the time. The water that's flowing in and out, that's going out the drain of the fountain, gets pumped back up into it. That's just an entity. An entity is just the fluid that flows through our sims. It is the timing of the sim that we are interested of, and it is the delay that is the output. Okay, so flip back here. So let's go and do that hand sim example. All right, there we go. So this is what your homework's going to look like. It's a little bit of a simplification, but basically like this. I give you a table that looks like this one. It has interarrival durations. These symbols here, 1 over lambda. So oftentimes we use lambda as a variable meaning encounter rate. So 1 over lambda is the average time in between an event. And so in this case, the event is an arrival. So this is saying here that for this example, I've provided you at least 4 interarrival durations. Theoretically speaking, these go on infinite, for infinite time. So you just keep drawing a new interarrival duration as you need one. But for the example I've given you, I haven't taught you how to draw things yet. So I'm just giving you that list pre-drawn for you. Same thing with service durations. This says here that they're distributed like mu for mean. That is the average time. And so this is saying that there are 5 service durations I've given you, but 4 interarrival times. I've organized them this way, not because I missed this one here, but as I explained earlier, I don't have an interarrival duration corresponding to the first customer. So that's why there is a gap here. So the idea is the first customer arrives, and then we're interested in how long between the first customer and the second customer. And that is this 4 under here. So that's why there's a gap there. It's an intentional gap. Under the service durations, the first customer does have a service duration. So when that customer hits the server, this is how long that customer will take in the server. But if that customer has to wait, then their total time in the system will be their waiting time plus this time. So this is only the time after the customer gets to the server. But if the server is busy, the customer has to wait in line getting up to that server. So that's why these are not the response times. The response times are the service durations plus the waiting times. All right, so that's how this table is interpreted here, and that's what I'm saying down here. I've just used integers here for simplicity, but they normally would be real numbers. So people arrive at any time. They could arrive at 0.5, they could arrive at pi, they could arrive at any time. But just to keep the math easier and to keep it more compact on the screen, we just use integers for these hand simulation examples. And that's probably what I'll do for final exam and midterms as well, is just to use integers. But that's not realistic. It's just to make the math easier. Like I said, the first customer has no interarrival duration. All right, that's an overview of that. Any questions about this table? Okay. There are state variables that you have to hand simulate. I already defined these earlier in the intro, talking about the homework, but just to make it clear here again, LQ at any particular time is the number of customers waiting for service. It theoretically could be infinite, anywhere from 0 to infinity, but it is going to be a whole number, and then LS is the number of customers in the server. There's only one server in this system, so this can only be 0 or 1. So it'll never be 2, never be 3 or anything like that. Because if we had multiple servers, we can do that. We can build a system with multiple servers, but for your homework, it's a single server node. So there's only one server, only one capacity. Cumulative statistics you have to keep track of. So in my example, I don't have F in here, but you do have to keep track of F, which I defined earlier in your homework. But I am going to show in this example in D, the number of departures, and S, which is the total response time for all customers served. And like I talked about earlier, at the end of the sim, you could divide S by ND to get the average response time for a customer. That's why we keep track of S. But as we're moving through, We don't know what ND is going to be at the end, so we just keep track of ND, basically the denominator and the numerator of that average separately. That's what we're doing here with these cumulative statistics. And the response time is the duration of time waiting plus service. So we're going to calculate response time by saying the time they exited the system minus the time they arrived at the system. And that will capture their service time and their waiting time. Questions about these definitions? Okay. So we have to build these records to put in our checkout line. And these records are these little records with two fields, the customer ID and their arrival time. So as a customer arrives, they get moved into the checkout line. That is a state variable keeping track of how many customers are being serviced at the head of the checkout line or waiting behind them. And so each one of those, we have to keep information, these little attributes, post-it noted on top of the customer. And one of their attributes is just their ID. So we're just going to increment that, customer one, customer two, et cetera. And the other is their arrival time. So when the customer arrives, we are going to lose track of when they arrived unless we stamp them with their arrival time. And that's why we add that up. So you're going to see these records down here that look like this. So this says customer one arrived at time 0. So you can see, you might see C6, comma 15. Customer 6 arrived at time, whatever I said, 15. So that's this record. The waiting and service area. So we keep track of them in this checkout line, this waiting and service area. So we're going to put all of these customer records in here. So down here in the blue, this is saying there are 3 customers currently in the system. Customer 2 is actually in the server. They arrived at time 1. Customer 3 is waiting for service. They arrived at time 2. Customer 4 is also waiting for service. They arrived at time 8. So our checkout line, this here checkout line, is going to have these lists in it. It can be empty. If there's nobody in the system, it'll just be an empty line. There'll be nothing in that cell of your table. If there's only one person in the server, there'll just be one of these records in it. So we're just keeping track of who's there. And this will become more clear, I think, when we do the example. And then there's the future event list or the event calendar. It has its own records, which are the types of events that happen. There are only 3 types of events in this system. There's the end event, which ends at time t. There's an arrival event. And so the way we read this is we had an arrival at time t of customer CI. So there's going to be a little bit of redundancy because you're going to see that in the checkout line, customer 3 arrived at time 10. Well, there may then be an arrival event that you're going to see elsewhere in the table that represents when they arrived or when they were scheduled to arrive, and it will say that same information, that A10, C3. That'll be that customer 3 is scheduled to arrive at time 10. So when that arrival happens, the arrival event record is going to go away. And then that information is going to get saved in the checkout line and being stamped on the customer itself. So if you look across the table, it'll seem like you have redundant information. But remember that the SIM can't see across the table. The SIM can only see one row at the table at the time. And that's why it'll look redundant to you looking at it from a mile-high view. But when you're actually looking at it from the SIM's perspective, that's why we have to keep track of these things. And then we have departure events. So this is when is a departure scheduled? And so this is saying there's a departure scheduled at time t of this customer. And this will become clearer, I think, as we do this example. This is what the future event list is going to look like in a row. So every row will have a different future event list. That's another check. You should never have exactly the same future event list, because the thing that moves you to the next row is the future event list, and that will, at a minimum, remove the first event from the future event list. So every row is going to have something that looks like this, and this row, it's saying the next event. So the next row will be at time 11, and it will be a departure of customer 3. And then this is saying that we know at time 15, there will be an arrival of customer 5, but we don't know until later if more events might get added in between here. So these are only the events we know will happen, but after the departure of customer 3, other things could happen that will insert things in front of this arrival. So this isn't necessarily the next thing that happens, but is a thing we know that will eventually happen. All right. So again, I think this will become clear when we do the example, but if there's specific questions that yeah, absolutely raise them. But then as we get to the example, then definitely raise the questions. So so what we do, every row of this is this logic. If you get an arrival event, you look to see if the checkout line is empty. So that would only happen if LS plus LQ is equal to 0 for that row. If that's the case, the checkout line is empty, then this arrival goes into the server. So LS will go up by 1. And then we're going to schedule the departure of this customer by the service time that we get out of this table. So this customer has an 8-minute service time. So we're going to take the current time plus 8 and we'll schedule that departure into the future. That's what we do on an arrival event if the checkout line is empty. If there otherwise are already individuals in the checkout line, so someone's using the server, then all we can do is add this customer to the end of the checkout line and increase the count of customers waiting in the queue. So LQ goes up. And then we always make sure our new customers in the checkout line, they're either at the head of the checkout line or they're waiting behind someone. And we always, because this is an arrival event, schedule the next arrival event, or else our simulation is going to stop. And so that will require going up to this first row of the table, grabbing the next interarrival, adding it to the current time to get our next event. Questions about this arrival logic? Okay, so the next event might have been an arrival, or the next event might be a departure. So what do we do in a departure event? Well, we always do in a departure event, it was increase the number of departures. Because a departure event happened, it's a count of departures, always happens. What we also do is we look at the current time minus the arrival time for this customer. That is the response time for this customer. And we take that response time and we add it to the growing list of response times. I just want to emphasize, this is not the service time. Sometimes it will happen to be equal to the service time if this customer was lucky enough not to have to wait. But if this customer had any waiting, if they waited in line at all, this will be larger than the service time. After that, we get rid of this customer from the head of the checkout line. So that means we can reduce the number of customers in the server by 1. But then if there's happens to be customers left in the checkout line, we can immediately bring them into the server. So we can undo what we just did and we'll add that 1 back, but then we'll instead take the 1 away from those waiting in the queue. If someone has just entered the server, then we know that an activity has started. Whenever an activity starts, we have to mark the end of the activity by scheduling it. So we look up at our service time distribution, and we, just like we would at an arrival event, schedule this time plus the service time, that's our departure. And then we can, and this is just saying the same thing I said there. Any questions about departure logic? And then the last event we have to process is the end event. So if you hit the end event, you can stop. So if you want on your sim, you can draw a. I think I state in the assignment what I want you to do explicitly. So follow those instructions. But you can imagine that if you see an end event, you could actually just stop the sim without creating an end event row in your table. And I think that's what I tell you to do in the sim. But it's okay either way. But the key thing is that do schedule things after the end event if they should be scheduled after the end event. So if the end event is at time 10 and you want to schedule something at time 15, go ahead and schedule it. Add it to the FEL, even though you know that you're not going to process that. The simulator doesn't know it's not going to process that because it's very greedy. It only looks at the next event. It doesn't look downstream to see like, oh, is it even, do I even need to worry about this? Don't worry about that optimization. Just put it in there and you'll have a FEL that will still have things in it at the end. You'll just stop early and that's fine. Okay, so let's see what that looks like. So this is a table like the one you're going to generate in your homework. You're going to have an F column as well in your cumulative statistics, but otherwise it'll look just like this. And then you're going to have this up here, and I'm going to tell you the end time here. So I told you the end time. So the first thing you're going to do is add this end event to the FEL for your first row. This FEL should always be in time order. So as you insert things, remember it's what we call a priority queue, insert things in order so that the next item that you pull out of it is always on the left. So we're going to initially insert this here, but as we insert other things, it will displace it and move it over. So this FEL should always be in time order. So initially, all we know, there's this end event. We're starting at time 0 at this first arrival. So you can imagine this first arrival is sort of before the table. So you don't actually put the first arrival event anywhere because processing that event. That's how we're starting the scene. So we jump to that time. So the clock is equal to 0 here. And then we say it was an arrival to an empty system. Departure. So we say customer 1 takes a minute to go through the server. So that's the second row of this table. And so we're going to then add 1 to the current time. And that's where we get this departure event. So our FEL says that the next event that we know about is going to be a departure at time 1. And that will be a departure of customer 1. And now we know that there's 1 customer in the server. So we're going to increase this state variable from 0 to 1. And we're going to put the customer in the checkout line. Then schedule the next arrival because we just processed an arrival. So in order to know that we eventually need to process, so we go up to the interarrivations, grab the 4 that's red up here. We add that to the time and schedule the next arrival FEL. And so this becomes total FEL. That's pretty much all we have to do for that row. We're fill out the row and say that's time 0. That's everything that happened at time 0. Nobody's in the queue. 1 person's in the server. We've had 0 on the cumulative statistics, and that's our FEL. That's how we processed our first arrival event. And now we're going to go on and process this next departure event. Questions on that first row? Once you've done 1 row, just let the FEL guide you the rest of the way. The first event in the FEL is a departure event. So we go to time 1, that departure event, we pull that departure event off, and we go to time 1 to process that departure. And now we just have to think, what do we do when there's a departure? And say, well, we increase the cumulative statistic for number of departures. Departures have gone up. Add 1 to that. We increase the cumulative response time. So the response time for this one is its departure time 1 minus its arrival time 0. So that goes up to 1 as well. Remove it from the checkout line. It's removed from the system so we can get rid of it out of the checkout line, which will happen to empty the checkout line in this case. We can remove it from the server, so we decrease the number of entities in the server. And then that's all we have to do for that first line. So that first line, we didn't actually do any scheduling. We just, because nobody was waiting. So we had no arrivals, no customers waiting, so we didn't have anything new to schedule. We just got rid of the current customer, updated our cumulative statistics, and now we know our next event is this arrival. So right now, the system is sitting idle with no one in the checkout line from this departure time to this arrival. So for those 3 minutes, the system will be idle, and we're going to skip over that idle time and go to the next arrival, and that will be time 4. Questions about that departure logic? All right, so now we just process that next arrival. jump to the arrival, and we do just like we did the first row. So we schedule its departure because it goes directly into the server. So we went up to its service time, add 8 to the current time, which is 4. So we schedule this departure event at time 12 of customer 2. Then we add 1 to the server because we just pushed it right into the server. We put it in the checkout line because it's now in the system. And then we schedule the next arrival because whenever we process an arrival, we schedule an arrival. And then we're done. So that is our third row there. We've got 1 customer in the checkout line again, our next arrival scheduled. I happen to have a next departure scheduled. In time is still there. Our stats are as such. Questions on that row? And then let's just keep drilling down through it. So next event is an arrival at time 6. So we're going to jump to time 6 next. So what do we do in arrival events? Well, now the arrival event can't go into the server because it has to wait for the previous customer who is not finished yet. So at this point, we add them to the queue. We don't add them to the server. So we increase the number of entities in the queue. Then we add customer 3 to the checkout line behind customer 2. We schedule the next arrival, and that's all we can do. We have no idea. You could claim that you know that customer 2's service time is 1. You know, customer 3's service time is 1. You know the customer 2's departure time is 12. So you could claim that, well, I'm just going to schedule the customer 3's departure because I know what it's going to happen. But you're not allowed to do that. It might be for this system, you are clever enough to be able to simulate it in your head, but the computer's not that clever. And for a complicated system, it may be impossible to do that type of logic because there's a bunch of different processes will be interacting. So we just have to go things one step at a time. So we don't anticipate. You should only ever have 1 departure or 0 departures in your FEL. You should only ever have 1 arrival and exactly 1 arrival in your FEL. Okay, so we process the next event. So we finish that. The next event will be an arrival at time 7. We jump there. We do the same process, and there that's gonna have similar results as before. So now we have 3 that are waiting in line. But finally, now we're at that customer 2 departure. So we go through a departure. We do the same logic we did in the last departure. So notice now this response time. This is the departure minus the arrival. We know that this customer 2 arrived at time 4. So the current time is 12. 12 minus 4 is 8. S was our current accumulated response time. So 1 plus that 8 gives us the 9. We process that departure event. And I can go on through that. So let's just fill out the table here, and then let me pause then. So here, the last line of the table, I've hit my end event. Technically speaking, we could jump to time 15, and it would look exactly like row 13, but E15 would be gone, and that's it. But it's a little silly to waste the space. So, and I'm pretty sure the homework instructions also say this. I'm okay with you stopping here. Any questions about that process? That is basically the process you'll do for the second part of your homework. Okay. All right. So in that case, we'll end with another clicker. And so I'm going to make this a numeric. And the question here is how many arrival events should there be in the FEL at any time? So I'm looking for a number, 0, 1, 2, 3. So in the homework example, in your FEL, how many arrival events should you see in every FEL? And that's all I've got for you. So if you have any other questions, feel free to come up after. And otherwise, have a nice weekend. We'll see you next week.